a little refresher or reminder on those rules, tangent squared theta plus 1 is equal to secant squared theta. That's what you get if you take sine squared plus cosine squared equals 1 and divide everything by cosine squared. A little corollary to that would be is if you solved for tangent squared theta, in which case you'd get secant squared theta minus 1 is equal to tangent squared theta. So that's the substitution that we're going to make. Just going to kind of move this together a little bit more. It looks weird. So radical 3 times secant squared theta minus 1 d theta. So I'm going to distribute radical 3 secant squared theta minus radical 3 d theta. Antiderivative secant squared is tangent, so radical 3 tangent theta minus radical 3 theta plus c. All right. So then it's just a matter of cleaning it up a little bit. All right. The cleaning up is going to involve a little bit of reverse substitution, but and bearing in mind that we haven't accounted for the bounds yet, we're going to need to reverse substitute back in the form of x unless we convert over the bounds from x's to thetas, which is, it's a matter of preference, right? Because we have a relation that allows us to convert from x's to thetas. So you can do it either way. So if you do this way, in fact, we would have dropped the plus c. We would need some new bounds. I'm sorry, should have put the wrong thing there. We would need some new bounds in terms of theta. Or we can go through the process of swapping it out, in which case, we know tangent here. Let me go with the orange. Tangent is this. So we could say radical 3 times radical x squared minus 3 over radical 3. So we get a little cancellation there, a little something. Minus radical 3, then I need a theta, so I might snag this one here and take the inverse secant of both sides and say theta is equal to the inverse secant of x over rad 3. There's other things that we could write, but that's the one that I would go with because it's already kind of tailor-made for us. And then that would get evaluated over the interval of radical 3 to 2. So x equals radical 3 to x equals 2. All right, so this is an either or situation. All right, so might as well do it both ways and see how it shakes out. Now, if I wanted to, and I do, I can figure out what the theta bounds would be. So let's get our theta bounds. Oh, bounce. Nah. All right. What I'm going to do is I'm going to go back to my triangle here and come up with a really nice ratio out of this. All right. Because I could get the secant ratio x over rad 3, but I could also get something a little bit more convenient for unit circle trig related stuff, and that would be cosine of theta is equal to radical 3 over x. So if x is equal to that first ratio, radical, well, I'll go top to bottom. So 2 and then radical 3. If x is equal to 2, then I'm looking at cosine of theta is equal to radical 3 over 2. If x is equal to radical 3, then I'd have cosine of theta equal to, whoop, I put an equal in a weird place there, radical 3 over radical 3. Right, which is a 1. But I'm going to shrink this down a little bit so it's not too crowded. I mean, it's already pretty crowded, but you get the idea. All right, so then we would just have to think about, well, where is cosine equal to radical 3 over 2? That would happen when theta is equal to pi over 6. All right, that's the first quadrant one. And the second quadrant, actually fourth quadrant one, 11 pi over 6, because it's a positive ratio. All right. As opposed to, make that a better looking one here, semicolons. Theta would be equal to 0 or 2 pi, or any multiple of that. So then I would want to be thinking about, okay, well, which one or ones are gonna make sense here, all right? So what I can do is I can go to my calculator, graph the original function, or at least the original integrand, and let's see here. We're gonna have the square root of x squared minus 3, and that's over an x. I'll just put it in as y3 because I have my derivative set up in y2. I'm going to actually turn off the first two because I don't want to delete them, but I also don't want to have them on and in the way. All right, now I only want this to graph over the interval of radical 3 to 2. All right, so zoom 6 I'll start with, but then my domain should be going from radical 3, x min radical 3, x max 2. And you see it's pretty tight around the x-axis. So what I can do is clear out, now that I have my domain in, clear out either the y min or the y max, doesn't matter, and then without hitting anything else, hit zoom 0, and it'll give you the best window for that particular graph. And then you can tweak it from there. Like maybe I don't want to go from 0.5 to 2.23. Maybe I want to go, oh, actually this can't be 2.23 because that's the min. So it's got to be scientific notation. Yeah, so maybe I just want to go from 0 here so I can see the x-axis. All right, maybe I don't want to start off at that. Maybe I do want to see the y-axis, but maybe I don't. It's really a matter of preference, all right, on that. But I like to restrict it to just the domain that we're given and see where that leads us. So this is the region that we're concerned with. That's the first quadrant region. All right, so if I'm thinking about theta values, I'm thinking about the ones that would be in the first quadrant. All right, so I'm thinking, ooh, that's a little large. On the high bound, pi over 6, the low bound, it wouldn't make sense to call that 2 pi because 2 pi is bigger than pi over 6. So I'd have to go with 0. It kind of forces me to go with 0 there. All right, so what I can do, so these would be the relevant bounds, is I can evaluate this function. I can do it both ways. I can do radical 3 tangent of pi over 6, just make sure you're in the right mode, minus radical 3, could actually just leave the radical 3 as a coefficient, times pi over 6, then subtract from that whatever you would get when you plug in zeros. As it turns out, you're going to get zeros, so it doesn't matter. So you get this decimal. I mean, maybe you want to go something a little bit more exact. If that's the case, you could do it by hand, pi over 6. And actually, I'm going to shrink this down a little bit so I have some room to operate here. Pi over 6 has a tangent value of 1 over radical 3. So I could say, so we'll have radical 3 times 1 over radical 3, tangent of pi over 6, minus radical 3 times just a clean pi over 6. If you plug in zeros for theta, it zeroes out, so that becomes irrelevant. So we're looking at 1 minus radical 3 times pi over 6. All right, so I'll just do a quick double check. 1 minus radical 3 times, I'll just pop it in this way, pi over 6. So you get that 0.093, blah, blah, blah. All right, and then, of course, the other way to do it would be to work with this monstrosity here. And I'll put a little bit more of a simplified version of it. Radical x squared minus 3. Slightly more simplified. Everything else is kind of the same. Alright, and so if you replace, no, I really need to shrink. So if you replace the x with a 2, you're going to get 4 minus 3, which is 1, so we're going to get a 1. Minus radical 3 secant, inverse secant of 2 over radical 3. All right, and so that's a weird situation. All right, but that's the same as saying the inverse cosine of radical 3 over 2. All right, so that's going to be a pi over 6. So 1 minus radical 3 times pi over 6. Now if I plug in a radical 3 for this piece, I get a 0. If I plug in a radical 3 here, I get the inverse secant of 1, all right, which is the same as the inverse cosine of 1, which is 0. So this whole thing zeroes out also for the second term, or for the second bound. All right, so this actually gives us the same answer, just maybe not in as aesthetically pleasing sort of way, if any of it is aesthetically pleasing. All right, so off camera, I'm going to clean this up a little bit more, but I won't waste your time with it. Number 5, it's definitely an interesting case because it doesn't seem to fit any of the rules that we have because it's not written as a binomial in the difference of perfect squares or sum of perfect squares sort of format. But what we can do is actually, and this is sort of a kind of a teaser for what we're going to do with partial fractions, or at least to some extent, is we're going to learn or review, depending on where you've been in terms of your content knowledge for pre-calc, is we're going to write this as a difference of perfect squares or sum of perfect squares. Right? And the way we do that is by completing the square. All right, so I'm going to take out just the radicand, 8 minus 2x minus x squared, and I'm going to set it equal to 0. You set it equal to whatever you want. I choose to set it equal to 0. You just need it to be equal to something, a little placeholder. All right. I'm going to reorganize things, but before I do that, I'm going to subtract off an 8. But I'm also going to, in the process, just move some things around. So negative x squared minus 2x. I'm going to leave a little space to complete the square and make that equal negative 8. All right. Now, there are a bunch of different ways to complete the square. The method I like is using the rule b squared over 4a. So I take my b value, there's an understood 1 here, so that negative 1 becomes my a. So negative 2 squared over 4 times negative 1 is going to be a 4. All right, well, 4 on top, negative 4 on the bottom. So that's actually going to simplify. I shouldn't have said 4. It's going to simplify to a negative 1, which is nothing like a 4. If I subtract 1 from one side of an equation, I can't just do that without subtracting it from the other. So on the left side, what I can do is factor out a GCF, factor out a, so we'll have negative 1 times x squared plus 2x plus 1. We'll have a negative 9 on the other side, which we could then write as negative 1 times x plus 1 squared equals negative 9. Bring the 9 back, we have 9 minus x plus 1 squared equals 0, and we can now use this to replace that trinomial. Now I can replace the radicand. I got my dx. Can replace the radicand with a 9 minus x plus 1 squared. And now I have something ready to rock and roll. This is in the form of the square root of a squared minus u squared. So I'd let a be equal to 3 and u be equal to x plus 1. Alright, so we place this appropriately, and appropriately meaning that the missing side after the placement of the two relevant pieces would be the square root of a squared minus u squared. Alright, so if I put the a value as the hypotenuse and the x plus 1 as one of the missing sides, I could put it here, which would create a cosine ratio, or I could put it here, creating a sine ratio. I prefer the sine ratio. So I'd say sine of theta is equal to x plus 1 over 3. So 3 sine theta is x plus 1, making x equal to 3 sine theta minus 1. Differentiate, I get 3 cosine theta d theta. Alright. The missing side, you know what, I'm just going to steal it from here. The missing side is the actual radical. Alright, so if you square each part, square the 3, you get a 9. Square this, you get this squared. 9 squared, or 3 squared minus this squared gives you that. Alright. So if I get the ratio of the radical to the constant, that's adjacent over hypotenuse, and that would give us the cosine ratio. Cosine of theta is equal to the adjacent side. Let me try to make this look a little nicer. Over the hypotenuse, which is a 3. So if I solve, I'm going to get 3 cosine theta is equal to that radical. Not what I wanted. Good enough. Alright, so I can make my substitutions now. And that would be 3 cosine theta replacing this, and 3 cosine theta d theta replacing that. Alright, so it's actually a pretty nice looking situation. Alright, so we have 3 cosine theta d theta over 3 cosine theta, which is going to give us a 1 d theta. Antiderivative is theta plus c. Alright, so then it really is just a matter of saying, okay, well, let me get a nice convenient ratio from the triangle. I'm going to take this one, if it lets me draw the ellipse, okay. I'm going to take the inverse sine of both sides, so I'll have the sine of theta is equal to x plus 1 over 3. Take the inverse sine, and so theta would be equal to the inverse sine of x plus 1 over 3, which is pretty not bad in comparison to some of the other problems that we had to do. So that's what my theta is going to transition into. Oh, I thought I hit copy, but I guess I didn't. Penmanship looks pretty bad. Plus C, and there it is.